Good evening and happy Thursday. Last evening, we introduced the derivative, right? We looked at the definition of the derivative as well as the definition of the derivative function. And we began to study rules of differentiation by looking at the basic rules, right? The constant rule, the power rule, the sum difference rule, and the scalar multiple rule. We're going to look at this evening 3 more rules. We're going to look at the product rule, the quotient rule, and then we'll look at the chain rule. Right, so product rule will let us find the derivative of a product of functions. Quotient rule, the derivative of a quotient of functions, and the chain rule allows us to differentiate a composition of functions. The derivative of a product of functions. How do I do the notation? Okay, to do that. Right? Many, when they first start studying calculus, would think and do think, oh, it's just this, the product of the derivatives, right? That is not what it is. Product rule says if you take the derivative of f times g, it is g times the derivative of f plus f times the derivative of g. And this has a natural extension, right? If you have a product of more than 2 functions, right? So the idea is you take one of the functions, take its derivative, multiply by the remaining functions, right? Plus, now choose a different function, take its derivative, times the remaining functions, plus choose a different function, so on and so forth, right? So you just differentiate each function and multiply by the remaining and then sum it all up together. And so I guess if you wanted, I'm going to use product notation. No, I won't. was actually going to be more difficult to write out than I originally thought without using product notation. Let's just do it this way. Actually, I need to do it this way. That's going to be really ugly to write out. Ignore the general part. I'm just going to show you three. All right, so this is for 3, which I'm just going to move up through the power of technology. Now you can see how it would extend then if you have 4 functions, right? If you have 5 functions, so on and so forth. Quotient rule. Derivative of f of x over g of x. Again, before seeing product rule, I might be tempted to think, oh, it's just the derivative of f over the derivative of g, which is, again, not the case. It'll be g times the derivative of f minus f times the derivative of g all over g squared. So we're going to be given several functions that we want to find the derivative of. Right? We have a quotient, so we're obviously going to be using quotient rule. Right. G of x times the derivative of f minus f of x times the derivative of g of x all over g of x squared. Two x plus 1 times the derivative of x squared minus 2. What is the derivative of x squared minus 2?
X.
It's just 2x, right? Right. Now minus x squared minus 2 times the derivative of 2x plus 1, which is what? Just 2. Right, now it's time for some algebra. So we can factor out a 2. Distribute that x through. And then just going to be minus x squared plus 2. Right, 2 times x squared plus x plus 2 over 2x plus 1 quantity squared. And that looks like as simplified as it's going to get. So there's our derivative. Okay. Now for this next one, there's actually two methods. First way to do it is to use product rule, right? So product rule. G times the derivative of f plus f times the derivative of g. Derivative of 1 over y squared minus 1 over y to the fourth. If you need to rewrite it, why is that highlighted? And it's y to the minus 2 minus y to the minus 4. Negative 2 over y cubed plus 4 over y to the fifth, isn't it? It's going to be plus 1 over y squared minus 1 over y to the fourth. Of course, now times the derivative, y plus 5y cubed. One plus 15y squared. Right? Let's try and simplify. Right, FOIL out each term. Negative 2, 18, 19, 4. 4 over y squared. Plus 3 over y to the fourth. Looks like plus 5. Okay. Now, since the problem was written as a product, I would be okay with that. Unless the problem said to fully simplify your answer. Second method. Simplify the function first. In other words, FOIL that out. It would be 1 over y squared times y. One over y squared times 5y cubed. Negative 1 over y to the fourth times y. Negative 1 over y to the fourth times 5y cubed. Five y minus 4 over y minus 1 over y cubed. And now differentiate. Five plus 4 over y squared plus 3 over y to the fourth, which you should notice is exactly what we got when we fully simplified after using product rule. Right? So really, if you're looking at a product of polynomials, right, you don't actually have to use product rule, do you? I should be careful because that first one isn't technically a polynomial. Right, so if you're dealing with the product of, what do I want to call them? Let's call polynomials that do not require integer degrees, integer powers, right? So anything of this form. You don't have to use product rule because you can always do algebra first and expand it. Right, so generally speaking, what you want to do is just follow the number one law of physics, the path of least resistance, right? You want to expend the least amount of energy possible. That's typically how I solve problems. I generally like to take the path of least resistance, the easiest path. And the whole point of this section is to get used to product and quotient rule, though. So I'll be sticking to product rule just so we get the hang of it, because there are going to be functions in the future that you have to use product rule on. Let's get one of these. All right. This is quotient, right? be the denominator, g, times the derivative of the numerator. Derivative of root x half x to the minus half minus, I'm going to write it this way. Numerator, x to the half. Oops, what's going on? Times the derivative, now the denominator. Derivative of 2 plus x. That's actually very simple, right? Derivative of 1. Right? All over the denominator squared. Factor out common terms. So I'm actually going to go ahead and factor out a 1/2 x to the minus 1/2. Leaves us with 2 plus x for the first term, right? Minus b2x. So in the denominator, we're going to have a 2 square root of x times 2 plus x quantity squared. And what are we left with in the numerator? A 2 minus x, isn't it? All right. What about this function? So what do you think we're going to have to do here?
I assume we'll use the quotient rule.
Quotient rule? All right, show of hands. Who agrees? Quotient rule. Okay. Six. Yeah. Well, I guess they didn't. Oh, they took it away. All right, 7. And so more than half say yes, quotient rule. Okay. You can lower your hands. So let's do quotient rule. Denominator times the derivative of the numerator which will be 1 minus a half s to the negative half, right? Minus numerator times the derivative of the denominator over denominator squared. Oh boy. Okay. Now we're for some fun algebra. I can make this a little bit easier. S squared squared. That's to the 4th, right? Factor out at S. Here we're going to be left with S, so let's distribute it through. We're going to have S minus a half S to the 1/2. Here we're going to be left with 2, distribute it through. Negative 2 times S, negative 2S, then plus 2S to the half. All over that S to the 4th. So we can cancel these S's. That's nice. Numerator, we're going to have what? Negative S. Why did it just zoom in? All right, negative S. And then what? Looks like 3/2 S to the 1/2 power. all over s cubed. Factor out a half s to the 1/2 power. Three minus 2 root s. Let me write that as s to the 1/2 for now. I'll write them as square roots later. Over s cubed. Right, so numerator, we're going to have 3 minus 2s to the 1/2. Denominator, we're going to have a 2s. Right, and then 3 minus a half. 5 halves, right? If we just write this now with radicals, three minus 2 root s all over 2s squared times square root of s. A lot of algebra there. Not as bad as some other problems can get, but however, there is a simpler way of doing this. This one actually does not require the use of quotient rule. Look at the denominator. Isn't that a monomial? It's a single term, isn't it? We can simplify this function first. And write this as s over s squared, which is s to the minus 1, minus root s over s squared, which is s to the minus 3 halves. Now take that derivative. Negative s to the minus 2 plus 3 halves s to the minus 5 halves. Factor out an s to the minus 5 halves. All right, that's the smallest. Actually, factor out a 1/2. S to the minus 5 halves. Left with what? Negative s to the half. Negative 2s to the half, sorry, I factored out a 1/2. Plus 3. And look at that, you get the exact same thing with much less work. Right? It is very common that is when you see a quotient to immediately think quotient rule. Right? That is very, very common. However, as this problem demonstrates, just because you have a quotient does not mean you have to use quotient rule. Right? My comp sci people know this. You generally want to write a code that executes in the least amount of time possible, right? That's algorithm efficiency. But I actually saw a couple of reports on the big O notation. And I was excited because I haven't studied big O in a long time. No rude jokes. But generally speaking, no matter what you're doing, right? You want to do it in the least amount of time. Right? You're an independent contractor, let's say, right? And you're hired to do a job. Well, you're paid the same amount, whether it takes you a week or a month to do the job, right? So if you can do the same job in a week and it's the same quality as a month, wouldn't it be better just to do it in a week? Right? That's just how my mind has been trained, to always try and take the shortest path. That doesn't, of course, mean that I want to sacrifice quality. But I want to be as efficient as possible. And that can also help you in future classes if you're taking like a timed exam, right? You want to do the question in a short amount of time as possible. Right, we look here at this problem. Yeah, that's what I want. And I go, oh, bummer. I'm going to have to use quotient rule here. Again, technically, I don't have to. I just don't have chain rule yet. Right? Denominator times derivative of the numerator minus the numerator times the derivative of the denominator. All over denominator squared. I mean, I can try to make things a little bit simpler by factoring out a 3 from the first and a 2 from the second. Problem is, I'm going to have to redistribute those anyway. So I might as well just keep them in there and get this over with. Expanding out the first term. Get 3t to the fourth plus 3t squared minus 12t cubed minus 12t plus 9t squared plus 9. Like that delimiter. That looks better. Then we get 2t to the fourth minus 4t cubed plus 6t squared minus 12t. And even with lines, I can't write in a straight line. Oh, joy. All over the denominator. So what? T to the fourth, so 3 minus 2, we're going to have a t to the fourth. 3 and 9 is, let's do cubes. Negative 12 plus 4. Negative 8t cubed. T squared, we're going to have 3 and 9 is 12 minus 6. So plus 6t squared. Negative 12t minus negative 12t is 0, and then we're left with a plus 9. Oops. Why did that not take everything? Whatever. T squared. So there we go. All right, so again, here we're going to have to use the quotient rule. But again, take note, just like we looked at a problem like this last evening. A, B, and C are just real numbers. They're constants. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Right? All over denominator squared. There's an A common. Right, I noticed that the remaining terms, when simplified in the numerator, are all going to be negative. Just go ahead and factor out that negative. And there we go. Now what we can do, and this is very common in more advanced fields, so when you move on, A, B, and C are all constants, right? But isn't a constant times a constant still constant? Right, so what you see is we'll often define new constants, right? Just so we eliminate the number of times we're writing it, right? So instead of writing AB, we'd rather write D. Right? Instead of writing 2AC, we'd rather write E. So you'll see that sometimes as well. I actually could have also just gotten rid of the negative, right? And incorporated the negative into those constants. Okay. So I'm going to use product rule here, just so we get the hang of it. Second function times derivative of the first function plus first function times derivative of the second function. And since these are fairly simple polynomials to work with, let's just go ahead and expand it out and simplify. Three x to the fifth plus 3x cubed plus 3x squared. And that'll be what? Plus 3x to the fifth plus x cubed plus 15x squared plus 5. Six x to the fifth plus 4x cubed plus 18x squared plus 5. Wait for this to bloody update. Hey, it finally updated. Right? Right? Oh. Well, here we have a quotient. Right? Immediate thought would be to use quotient rule. But that really wouldn't be the most efficient method, would it? Simplify this function first. Now take its derivative. This is just a simple sum difference power, right? Factor out the x to the minus 3/2. Factor out a 1/2 even, x to the minus 3/2. 15x to the third. Minus 3x squared minus 1. And that'll be over 2x root x. What just happened? Why did... Oh, Teams is doing this again where it's automatically breaking up recordings. Oh, joy. Absolute joy. All right, so let's take a moment. And examine this problem. All right, so let's think about this problem for a little bit. How would you want to proceed with this? Because there are several ways we can go about this. So what are we thinking? How? How would you simplify this? Right? So that is one way to proceed, and that is the easiest way to proceed, in fact. Right? Is by recognizing that you have z squared minus 4 is a difference of squares, z squared minus 1 is a difference of squares, and then this is going to simplify very nicely. Right? What we're going to be left with is simply z minus 2 times z plus 1. Right? And now what you could do is expand this out. But I'm actually going to use product rule here. Because each has a derivative of 1. Right? We're left with z plus 1 plus z minus 2, which is just simply 2z minus 1. What we could also do here, right, is we could treat this as a product rule. But then we're going to take the derivative of a term, right? Each of those individual derivatives is going to involve a quotient rule. We could also think of this as a quotient rule, right? But the derivative of each function is going to require product rule. And those algebraically are really, really messy. Are there any questions on product or quotient rule? No. Okay. Let's see if I can find. No, those are boring. About here. Oh my, that's just going to be bloody evil if I do that. I like it. We're going to find the derivative of this function. But before we can do that, we're going to have to simplify that denominator. There's the first term. And there's the second term. Oops. All right, so what are we going to have in the denominator? It looks like a 2q cubed plus 6q and that's under q squared plus 3. Now we can go ahead and use quotient rule to find this derivative. Denominator times derivative of the numerator minus the numerator times derivative of the denominator. All over denominator squared. Which equals I have what? 4q to the 4th plus 12q squared when you expand out the first term minus 6q to the 4th. We have a 6q squared, 18q squared, and then 18. Negative 2q to the 4th. That's what, 24q squared, so minus 12q squared, then minus 18. Right, so we can factor a negative out. We can also factor out a 2. You can factor out a 2 squared from the denominator, right? That's where the 4 came from. Ooh, if I do that, so if I factor out negative, I'm sorry, these should be positive. Oh, I think this is going to be nice. I can also factor out a q squared from the denominator. And then isn't this look at that. We're going to be left with just negative 1 over q squared. Or negative 1 over 2q squared. How nice is that? Right, because the problem also wanted us to find the second derivative, which now is easy. Would just be 1 over q cubed. See that? So now we're starting to see more and more algebra creeping into the problems. All right, so before we go on our break, I have graded your first tests. If you take a look at the comment on the test, the general comment on the test, you will see your current grade in the course. Right, I will do that with every unit test. I will comment what your course grade is up to that point. Right, you should be able to see your individual scores on each question and comments just by going into the gradebook and opening up the assignment, clicking on that form link. It should bring you back to the comments. So when we get back at 7:50, we are going to look at the chain rule. So I will see you all at 7:50. And we're back. Hopefully, no more technological hiccups. That would be nice. Moving on to chain rule. This rule is one of the most important rules, and it is also often the one that is used incorrectly the most. ddx of f of g of x. It's the derivative of f evaluated at x equals g times the derivative of g. Right, so written another way, f prime of g of x times g prime of x. You may also see it written this way. Oops. F prime of u times u prime. With chain rule, we can now rewrite the power rule to be more general. Called the general power rule. Derivative of u to the n u to the n minus 1 times du dx. You can also think of chain rule. Are you serious? As change a variable. And OneNote is being weird. There we go. So again, we're going to be given several functions that we want to find the derivative of. So the idea is we want to write this as a composition, or we want to do a change of variable. Well, our inner function, right, is 5x to the 6th plus 2x cubed. Then du dx, right? So that derivative is 30x to the fifth plus 6x squared. Right? F of x now becomes u to the fourth. This means that f prime for u cubed times du dx now resubstitute everything in. 4 times 30x to the fifth plus 6x squared, right? So this is the du dx, and then this is the u cubed times 5x to the sixth plus 2x cubed cubed. Okay. Right, so that's one notation. Let me give another notation. So another way to look at this is write your function as a composition of functions. So let's say g of x is our outer function. Be run over cube root of x. Let h of x be the inner function, the x squared minus 1. Then notice that f of x is g of h, which means that f prime of x would be g prime of h times h prime. g prime of x. Well, another way of writing 1 over cube root of x is x to the minus third, right? So g prime be negative 1/3 x to the minus 4/3, or negative 1 over 3x cubed, 3x times the cube root of x. H prime of x is just simply 2x. Therefore, f prime, look at g prime. Replace x with what we said h was, x squared minus 1. Now multiply it by h prime. There's your derivative. Either notation is fine, right? Whether you want to do u or you want to write a composition of functions. And it's whatever makes more sense to you. Now, generally speaking, I do chain rule in my head. And so let me show, or not necessarily show, because I can't really show you what's going on in my head. I'll use this next problem to explain my thought process the way I do it. Okay, so here's how I typically tackle derivative problems. First, I look at the function. And I look at the overall picture. And I go, okay, what kind of function am I dealing with? I'm dealing with a product, right? I see a product of functions. So I'm going to use product rule. Right? So what does product rule tell me? I'm taking the second function and I'm multiplying it by the derivative of the first. So now I want to look at this function here. I'm taking its derivative. So again, I look and I go, what kind of function am I dealing with? It's a power function. Well, power function is 3 times the function to the power minus 1. Times the derivative of what's inside. So I need to multiply by the derivative of x squared plus 1, which is 2x. Right, but I'm still in product rule. So plus the first function times the derivative of the second. Right? So now I'm looking at this function here. I play the same game. I go, okay, what kind of function am I dealing with? I'm dealing with a power function. Derivative of a power function. Power times the function to the power minus 1. Now I have to look inside and multiply by its derivative. So the derivative of x squared plus 2 is 2x. And there's the calculus. Now we just have to do algebra. Factor out common terms. Let's see. There is a 6x common. And there's a 3 common from the constants, a 2x common. For x squared plus 1, I have power of 2, power of 3. I factor out the smaller power. X squared plus 2. We have power 6, power 5. Again, you factor out the smallest power. And now what's left? From the first term, just an x squared plus 2. From the second term, 2 times x squared plus 1. And so there's the derivative. So those are 3 ways of doing chain rule. Again, I do not care which way you do. Whichever way is easiest for you. Right. So again, take a look. We're dealing with a product, right? So we're going to wind up using a product rule. Right. So then at this stage, you have to decide, well, how do you want to approach it? Do you want to do composition of functions? Or do you want to do U sub? Right. By the way, the third method I gave, the one where how I explained how I do it in my head, that is essentially using the U, change a variable. I just do it in my head instead of writing it out. Right. So I guess what I could do is, let's write this in green. General product rule. Actually, this isn't going to be a general product rule, is it? It's just another way of writing FG crap. I don't think there's a general. I don't think I can write general product rule using chain rule. Once I do f of u times g of v, that might work. I don't want to make it more complicated. So if you want to write this out, right, you know what you're going to need is you're going to need the derivative of both of those functions. Right, so start there. Let u be t plus 1. Du dt is obviously then just 1. Then the derivative we're looking for is now d dt of u to the 2/3, which is a general power rule. Right, 2/3 u to the minus third times du dt. 2/3 t plus 1 to the negative 1/3. So keep this one in mind, right? Because that is the derivative of the first function that we need for product rule. Right, now we want the derivative of the second function. Well, I'm going to use a different variable here. I'm going to say v. Right, let v be 2t squared minus 1. Means that dv dt would be 4t, right? So what we're now looking at is the derivative with respect to t of v cubed. 3v squared times dv dt. Replace v. There's our second, or the derivative of the second function. Right, and then it's at this point literally just copy and pasting, right? So h prime of t, product rule. Second function times the derivative of the first function. Plus the first function times the derivative of the second function, which we also found, right? That was up here. Now it's just a matter of algebra. Let's factor out common terms. 2/3 I see is common. T plus 1, the negative third, and then 2t squared minus 1 squared. And then what are we left with? 2t squared minus 1 plus 36 over 2, 18. Times t plus 1. Like that. You can leave it like that. That's perfectly acceptable. Right? We could also write it this way. Either way would be fine. something real quick. No, that didn't even fix it, so I don't know what. I don't know how to fix that stupid freaking bug. All right. F prime of t. What's going on? It's not battery power, so why is my screen so dim? Technology is really not my friend today. There we go. This is a product rule. Second function times derivative of the first, which is a power function. So general power rule, 4 times the derivative. I'm sorry, 4 times the function raised to the third power, and then times the derivative of the function, which is 3. Plus the first times derivative of the second, which is again a power function, general power rule. Power, -3, times the function to the power -1 times the derivative of the function. What do we have in common? Looks like a 6. And for 3t minus 1 cubed, for 2t plus 1 minus 4. That was 12. So that's a 2 times 2t plus 1 minus 3t minus 1. Four t minus 3t, and then 2 plus 1. Yeah, so 6 times 3t minus 1 cubed times 2t plus 1 to the minus 4 times t plus 3. Oh boy. So again, look at this function.
Can you go back up, please?
I can. How far up do you need me to go?
Just till there.
So big picture. What kind of function are we dealing with here? So big picture, what kind of function is this? It's not a sum or difference. It's not a product.
Power.
The power function overall. So we're going to use general power rule. So it's the power times the function to the power minus 1 times the derivative of the function. Right? Well, now we look at it. We want to look at this bit, right? And we say, how are we going to take that derivative? Right? So again, what kind of function is that? Clearly, it's a quotient. So we're going to have to use quotient rule for this derivative. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Now keep in mind, this is all multiplication. We can factor out a 3u squared, multiply it by that 8. U cubed minus u cubed is 0. 1 minus negative 1 is 2. And we can simplify that to 48u squared times u cubed minus 1 to the 7th, all over u cubed plus 1 to the 9th. Okay. Right. Look at h of r. what rule are we going to start with? All right, so again, big picture. What type of function are we dealing with?
Quotient.
It's a quotient of two functions, isn't it? Which tells us quotient rule. Denominator times the derivative of the numerator. Now we look at the numerator and we go, since we want to take that derivative, what rule do we have to use?
Power.
Right, the general power rule. 3 times the function squared times the derivative of the function. Right, and that function is just a simple polynomial function. Minus numerator times derivative of the denominator. Well, the denominator is also general power rule, right? Five times the function raised to the fourth power, then times the derivative of the function. Again, it's just a simple polynomial, so its derivative is simple to find. Right, and that's all over the denominator squared. Okay, fun algebra time. For the constants, we have a 2 common. R squared minus 1, lowest power is 2, that gets factored out. 2r plus 1, smallest power is 4, that gets factored out. And then what are we left with? 3r times 2r plus 1 minus 5 times r squared minus 1 all over 2r plus 1 to the 10th power. Uh-oh.
Your screen froze.
Screen didn't freeze. It's the connection. I may have just gotten booted on my tablet. Let's find out. Stop sharing. Okay, so that went right away. But now it's not coming back up. Let me try leaving on my tablet and then rejoining. All right, I'm gonna have to restart my internet. Wow, that's lovely. Create your first avatar? No, thank you. There we go. I just had to reset my network connection on my tablet. And thankfully, I saw that before I got too far. That would have been a problem. Right. Where did it stop? I think it stopped like right here, didn't it? Like I got to this and then my network stopped.
Yeah, you wrote the 3R times 2R plus 1, and then it stopped.
Okay, and then it stopped from there. Right, so like I said, thankfully didn't get too far ahead. That's nice. Well, looky here. They simplify. It's going to have a 6r squared minus 5r squared. So that's just r squared, right? Then we have plus 3r plus 5. Two r plus 1 to the 6th power in the denominator. And there's our derivative. Right? Right. So some of these can start to look quite intimidating. Right? What I find a lot is students really do try to overcomplicate it. All right, they're trying to do way too much at once. But I'm trying to break it down the way I am, where I say, look big picture, right, and just go one step at a time. All right, so again, we look at big F. We look big picture and we say, what rule are we going to have to use? Again, this is a quotient, right? So start there. Start with quotient rule. Right, so now you know where you're starting. You go, okay. So what does quotient rule tell me? Quotient rule says we're going to take the denominator, multiply it by the derivative of the numerator. So now you look at the numerator function, t squared. Well, that's a really simple derivative take, right? That's just straight up simple power rule. Then quotient rule says you subtract the numerator times the derivative of the denominator. All right, now you look at the denominator function and you go, what kind of function is that? That's a general power, right? Because you can rewrite the square root as power 1/2. So general power. And then you look and you go, okay, what does the general power rule tell me? And it says you bring the power down times the function to the power -1. Then it says multiply it by the derivative of the function. Why did I write squared when that should be cubed? Oh dear. Helps if you write it down right. All right, so now we want the derivative of t cubed plus 1. That is a simple polynomial. All right, remember what we were doing last evening with simple polynomials. You just go term by term. T cubed has derivative 3t squared. 1 has derivative of 0. Quotient rule then says you square the denominator. And by the way, that is your calculus step, right? Everything that follows from here is now algebra. So that's your only calculus step. There's a t common. There is a t cubed plus 1 to the -1/2 common. I also need to factor out that 1/2. And now what's left? That's going to become just t cubed plus 1. I'm factoring out a 1/2 t from that. That should leave us with 4. Minus, factored out a t, that leaves us with t cubed. And that leaves us with 1. cubed plus 4, right? 4t cubed minus 3t cubed, right? And then plus 4 over 2 t cubed plus 1 to the 3 halves. I'm going to leave it as 3 halves. I don't really feel like writing as t cubed plus 1 times the square root of t cubed plus 1. I mean, I suppose I could write it this way. All right, just to get the radical limit and make it look like how it was presented. But there we go. There's our derivative. Are there any questions on the chain rule? Okay. Closing remarks. What I would recommend you do is have a separate sheet of paper and write down all the rules that we're going over. Right. So I'd write down the constant rule, right? The derivative of any constant is 0. Write down the power rule. Write down product rule, or write down some difference rule, right? Write down scalar multiple, product rule, quotient rule, and now chain rule. I would also include the general power rule. All right, if we take a look, what we will be doing on Monday is looking at exponential functions, logarithmic functions, and trigonometric functions, their derivatives, right? So when we do those, I'd write those derivatives down on that sheet of paper, right? I'd keep that handy. Right, this way you're not trying to flip through pages of notes to find what you're looking for. You have it all right there on one sheet. And then the Monday after that, because remember, we're not meeting next Wednesday or Thursday. We finish up with derivatives. All right, I need implicit differentiation in order to get to the derivatives of the inverse trig functions. Right, and then I'd write those 6 down, and that'll be it. That'll be all the derivatives. Right. So five things are due tomorrow night. Right, your first reflection assignment, the 3 assignments on My Open Math, and then the initial post on the limit. Right, you just come over to the discussion forum here. You're going to make a post, which no one has done yet. All right, so that's all due tomorrow night. There are 2 assignments tonight. 2 My Open Math assignments tonight. Assignments number 8 and 9, those will be due Saturday night. There's also a quiz tonight, but that is not due until Monday. Right. And then starting on Saturday, you'll then go back to the limit discussion, right? And you'll post your replies to 2 other posts. That will also be due Monday night, but that's 11:59 p.m. The quiz is obviously due at 6 p.m. Right. The reflection, the post, the replies, they shouldn't be difficult assignments. Right, so we got quite a bit coming up that's due. Again, as a reminder, we do not meet next Wednesday nor Thursday. Right, but we do meet on Monday. Is there anything else? Nope, I think that was it. Everyone have a wonderful weekend. See you again Monday evening.
Thank you.